Hello. Hello.
Wow. Hey, when there's some sound. Hello. Hello. Can you say that again? I think we changed to this.
Hello, check. Hello.
Yes,
Hello, check.
yes, I can hear it.
Yeah, so I think we can start, right?
Yeah.
Okay. This is you can remove the
Okay. Sure.
Okay, good morning and welcome everyone. I was expecting a little bit bigger class, but not many people are in this room. But how about the online? I think there's not many, but let's introduce let's start the tutorial. This tutorial is about the segment routing on the IPv6 data plane, so we call it SRv6. And my name is Awal and I work for APAN60 and we do training and technical assistance to our region, to our members, and we participate in different program events where we do workshops and trainings and conference talks. I would start with the presentation very soon, and we have a lab as well, so can do some testing. For the starting of the session, I'll just ask you to quickly go to the menti.com and join with this code. And before the presentation starts, this is something I want to do because this is morning and I want everybody to be activated. So let's do this very short slide deck. So please join menti.com with this code, and if you want, you can scan the QR code as well. Okay, I need that is maybe on that side, please. That
Yeah, but this actually can move by the
yeah. Okay. It's okay, but the screen can be on that side.
Yeah.
I need to see the question. Okay, so are you ready for the tutorial? Interesting that you don't have any option to say no, right? Okay, now where are you from? And select the location and submit, please. You still need to join. This is the QR, this is the code on top of the deck. Okay, all of us are from Hong Kong. I don't want to spend time much with this one. And how to say good morning in your native language. I want everyone's full attention and your activity. You have to type something. Is it Mandarin or Cantonese?
Cantonese.
Cantonese, yeah.
Mandarin, I think, still the same,
Say, oh,
but pronounced
pronunciation
different.
are different. Yeah, okay. Yeah. Great. How about this? From which industry you are from? university or NREN. Yeah, all of us from university. Do you have your own transmission backbone? Or it's just released, or you just take IP services from the provider, you don't maintain the transport network? This question is somehow really related to what we are gonna do today, segment routing. If you have your own backbone, it makes sense. Otherwise, you have the concept, you may ask your provider to do this, but you don't control it anymore.
But if we have an IRU,
Yeah,
we
yeah, of
still
course.
say that it should be still a lease, right?
Yeah, it's a good point, actually. I was thinking, how can I put a IRU contract core, not the fiber, as a lease? And how can I put here in the option? But if you are having a, let's say, one pair of core from the transmission fiber optic provider leased for a long term, that's the IRU, and you can basically think it as you own that for the time being, even though it's in business term it's leased,
Yeah.
but can think that you own it. But if you have that, that's very good, because for NREN or universities, this is the one of the best option you have, instead of really laying fiber and maintaining it and then change it after 15-20 years. I think it's better. Okay, so that was my last question, and I think for us it will be very good because we either own or lease the fiber, at least from somebody. So that might be very relevant to this workshop or tutorial. If you go to academy.apnic.net, somewhere in the event list, you should see the segment routing APAN60 event. So please click there. And the event page should look like this, but I need you to click on this tab, course materials. So this is basically today's event, and you have some information here, but I want you to take a look at this part, and this is the presentation I'm gonna cover, so you can download it and follow along. So this will be a PDF that you can keep on your screen on your laptop. And there will be lab. I'll probably try to do the Juniper one, but there is one Cisco as well, so you can practice it anytime. Your colleagues can do that, so share this link with them if they cannot join today. These are virtual labs. They can run it from anywhere as long as they have internet. Not so sure my audio is okay or not. Can you turn the volume a little bit, like this one? Yeah, a little bit. Is it okay? Okay, perfect. Okay, so I'm gonna start the slide deck now. Give me a moment. Yes. Because to cover segment routing, it has so many dependent modules to cover. So it depends on routing, it depends on routing protocols like IGP and EGP. It depends on MPLS concept, and then the segment routing version 6, and then also IPv6, and then the real concept of segment routing version 6, segment routing on IPv6 or SRv6 will be easy to understand. But I have only 1.5 hour theory session today, so difficult to cover all these prerequisite concepts. but I'll try to give you some backgrounds and so you understand how the SRv6 finally works and why it is so good compared to the previous different other technologies that network engineers tried, but to some extent they achieved, and then why this one is more convenient for the transport providers and telcos and NRANs and universities who are spreading their campuses in different parts of the region or the area. I might go and skip some of the concepts, but please feel free to stop me and say that, you know, this part I need to know more about. So I'll do some recap on MPLS and segment routing, and then how segment routing can be done with the IPv6 underlay. Actually, IPv6 data plane, not underlay. Okay, so MPLS recap. I'll try to make it simple so you can get the points. Then I'm going to skip many things. So in MPLS we have. So first of all, we understand how packet moves from one node to another. So it's basically looking at the destination address. So whenever and then I'm talking about routers on layer 3 devices, not really layer 2 at the moment. So just on layer 3, when from a source to a destination, a packet should move, it has to travel maybe one or many, you know, layer 3 devices if they're in 2 different networks. So every layer 3 device, or in short, I can call it a router, if it receives a packet, it basically look at the destination header information. And then it tries to look at its routing table and this find out which exit interface should I pass this packet out to help the packet go to the destination. That is its job. And now how the routing table is built is a control plane mechanism. So when now I split this concept into 2, and I think you already know this, that the router's 2 plane, control plane and data plane, needs to work together to make this happen. So control plane is like collecting the routing information even before the packet needs to move. It needs to know the destination's information first. So the routing protocol works at the control plane level. Then they form neighborship and then collect the routing information from each other and then build a table. It's sometimes called routing table, but later in smarter routers called also, there's another table called forwarding table, or forwarding information base or something like this. So this happens in the control plane level, but when the packet comes, the router needs to decide the packet should move to that interface or that interface or that interface to get out of my device if it is not to my router as a destination. Okay, if it is somewhere else, I'm just transit router. So this happens in the data plane. The packet or data moves, and this whole processing is the data plane task. And before that, the routing information is the control plane task. Now, this was at the beginning of the, not the beginning, but somewhere in the middle of the internet evolution, where there had been so many packets coming, but routers' routing capability was not that good. So a process dependent, the ability was dependent on the processing power. So if I have 10 routers to cross, every single router needs to check the address at layer 3 and decide which interface to go. The next router needs to check up to layer 3 and decide where to go. And so this is okay, but not okay when you have so many packets coming at the same time and your router is too busy. That is, I'm talking about, let's say 20 years ago, something like this. So the backbone providers were struggling to buy big routers, because without big routers, big number or large number of packets cannot be processed and forwarded very fast. So there had been a need at that time, some technology that uses less packet processing, but it still can do faster decision to from where it's to where I should send the packet out of my device. So that's between layer 2 and layer 3, there was something called layer 2.5. And that's layer 2.5 technologies is called multi-protocol level switching. So it's not really routing, not really switching, but somewhere in the middle. That's why it's so level switching or MPLS called 2.5 layer 2.5. So what happens with that is if a generic packet comes to a MPLS enabled router, it either it does one of these tasks. It either adds the level between layer 2 and layer 3, that's called push, means you are pushing a level to the packet and making it IPv6 aware packet or something like this. So this push happens when that's the first router of the MPLS domain. So before that router, that other router was not dealing with MPLS. So this is the first router, adding a level to the packet. So that's called push. And if you remove the level, of course, that's called pop. That's at the bottom. When you leave the MPLS domain or you don't need the level anymore. So what I'm saying, because there can be stack of levels. So there can be multiple levels stacked together. First level I need to remove. That's called pop. But I'm not removing all the levels. So every level when I'm removing, it's called pop. If I don't need that, just remove it. So that's called pop. So push is adding a level. Pop is removing a level. Swap is I want to forward. So when do I need pop? The transit routers who saw the packet with a level, but it knows that I need to send it to the next router, but it wants a different level, not that level. So I'll just remove the current one, I erase that one and put a new one. So I'm actually swapping the levels, not really removing or adding anything. Like the levels space is there, but the number will be different. So I'm not removing the space or changing the whole structure. Okay. So let's see this example and you'll see what I said, that how it works in control and data plane level is important because MPLS concept basically decoupled the control and data plane, which was previously together. So the control plane, the routing protocols, neighbor relationship, collecting routing information and things like that happens in the control plane. And then it finally build the routing information base. The level, when I'm talking about level, the level also needs to be collected. That means there has to be some other adjacencies. And talking to the neighbor saying, hey, I have this level for this route. Can you store it? So if you want to come to me, use that level so I'll understand what route you are talking about. So that happens at the level distribution protocol level. So there are now two different types of protocols. One talks about routing information, the other one talks about level information. And the level information protocol collects the information, put it in the level information base. Like routing information goes to routing table, level information goes to level table, something like this. And then finally, your forwarding information base has the routes or destination addresses, or your base path. The level information base, along with the the forwarding tables, it finally brings the level forwarding information base, which means this is the level table that will be used if the level packet comes. Okay, so there are now two types of forwarding tables. If you have IP packet coming, you look at your IP routing table or forwarding table. If a level packet comes, you look at your level forwarding information based on level forwarding table. So there are some terminologies you need to know before going deep into the discussion. This is MPLS domain. When I'm talking about MPLS domain, it's basically the collection of routers who participated in the MPLS network. So in an organization, if you have several routers understand each other with MPLS, they are your MPLS domain. The MPLS domain routers have different names, but it's not necessary for operations. It's just for our understanding. When we talk about some of this stuff later, so you understand what I'm talking about. Who are in the middle of the domain, not as an entry or exit points, they are simply called as level switch router. But this is also a level switch router, actually. This is also a level switch router. But why we change the name to different name? It's called level edge router because it's at the edge of the domain, but that's basically from the perspective of whether the packet comes from that side or not. So let's say IP packet entering my MPLS domain here, from here. So that's why it's my incoming or ingress level edge router. That IP packet now became an MPLS packet because this will add or push some level on the header. Okay. So, and then after that, it's just swap, means that intermediary routers will basically just change the level. And then finally, when it comes to the destination, the MPLS packet will exit and it will be like a normal packet. So that's called level edge router, but for egress or exit or when it leaves the MPLS domain. So that's why it's called. If the packet comes from that side, this definition, you can change like it. You can say this is the ILER and this is the. It's just the terminologies. When we are gonna talk about VPN or the layer 3 VPN, layer 2 VPN, I'm pretty sure that you have heard this, that MPLS can do L3 VPN, L2 VPN kind of thing. So when we talk about MPLS VPN, the router's names change a little bit. We call PE or provider edge router. And in the middle, they're like provider router. So there is no customers here. The customers are in the edge routers. If you have a customer on this router, it will also become a PE router. You can tell PE router. And again, these are just terminologies, no relation with the operation. Operational configuration, you have to configure based on what you need. And this is just for the definition. So how this level information is collected. So let's say this is my PE router, and I know I have a network connected to my router, and I want this router to, and I configured MPLS. So this is my MPLS domain. So when router R4 inform the neighbors that, hey, I have a network, you can come to me, but you can actually use MPLS level to come to me. So this R3, like it used to need to know this route, so this guy has to advertise, right? So this information needs to be advertised. Similarly, the level also needs to be advertised. So R4 will basically say, hey, I know this route and I use 300. So if you want to send a packet to me, you send the packet, the destination is this, okay, but you also use level 300 and that's what I want. That means the level is not decided by this router, the level is decided by this router and it's advertised to the neighbor. When this neighbor advertised the same route to R2, it will have its freedom to select its own level and it will inform. For example, R3 is sending R2, hey, this destination I can take you, but use level 200 if you want me to pass it next to the next router. And then next router similarly, so from here, going towards the upstream or going towards the uplink, okay? You can call it downstream, you can call it upstream based on the advertisement. Now, when the real packet comes, the real packet will come this way, and that's sometimes called LSP, level switch path. So level switch path means the path that the packet will take based on level switching. So if somebody wants to go any of the destination IP of this subnet, they will basically take this path because that's probably the best path. Now, let's say if we have VPN, what we'll do, we already see, like, if I want to pass or signal my level to the next routers, I'll decide my level and I'll pass it to my neighbors. They will decide and they will pass it and things like that, and finally it will come. But this example, I'm talking about a VPN that is between PE1 and PE2. So the intermediary routers or the P routers really don't need to know or understand about it. If it comes to me, I will understand it's actually my customer, let's say VRF this, or my customer's VPN this, number this. So this signal will happen between PE1 and PE2, no need to understand by anybody else. So basically what I'm saying again is I'm sending another level. That level indicates a VPN or a VRF, okay? So, and I want this between PE1 and PE2. So when the real packet comes, and as you can see that this one is basically saying that, you know, for this VRF or VPN, I'm using level 1, 2, 3, 4. So this guy will basically use 1, 2, 3, 4 if it wants a packet to go to this VRF or VPN. Okay. So what will happen is it is signaling that my in level is 100, no out level, because after that there is no MPLS. So I don't have any outbound level. I didn't receive it by anybody. I'm just originating it. So it's sending it to its neighbor saying that, hey, if you want to come to PE2, use level 100. This one created its own level and it's 200, but its out level is 100. So if anything comes with 200, it will basically send it with 100 because the 100 is the neighbor's advertisement. So this in and out basically is from the point of from the respective packets flow, not the level flow. For PE3, it sets the level 200 for PE2 and pass it to P2. And P2 received this 200 and built its ILM or incoming level mapping. It put it in the out level, but it generated its own level, which is 300 for that round. So to P3, it's 300, and then P2 going forward to both of its neighbors. And then let's say finally, this level comes here, and from that side as well, it will come here. So what happened is, in this example, because we are talking about BPL between PE1 and PE2, the level distribution happened with a protocol called Level Distribution Protocol, or LDP. How this message is going to that one? It's happening with a new protocol called LDP. So for MPLS, LDP is a requirement if you want to exchange level information. There are other protocols who are also capable to distribute levels. Capability of distributing level is an important aspect, important thing for MPLS. Because OSPF cannot do that. ISIS cannot do that. That's why we need a new protocol called LDP. BGP can, and we'll come to that later, but OSPF and ISIS was not sufficient to run MPLS. So another new protocol had to add. And every single router needs to be able to understand that. If you have PE2 and 5 does not understand LDP, your MPLS is going to be broken because your domain is now 2 MPLS domain, not one single domain. So that is a very something new that needed for MPLS. So this level distribution happened, and you can see that everybody can see from where it's coming and what is their level, and they can generate their own and then pass it to their next neighbor. And this way they basically distribute each other's level. Now, if you finally see how packet moves after this is like this. When the packet comes and wants to go to CE2, you see that PE1 is the first router in the MPLS domain. That means it needs to create the level switch path with the levels in between the layer 2 and layer 3. So basically it will push 2 levels now, because the top level, so this is the top level, this is the bottom level, and basically it will be easy to understand with this one. So let's say the packet, actually the payload came from a non-MPLS router, which is normal because the source and destination will definitely talk with the standard OSI layer concept or TCP/IP layer concept, not really the MPLS layer concept. So this is a normal IP packet, which is the payload, came to PE1. PE1 looks at the destination. Destination is PE2. And it knows that if I want to go to PE2, I have to go to P1. And who decided that? This is decided by the IGP, right? The OSPF or ISIS. That has, remember, I had a picture where we had feed, we had L feed. I need to go to PE2, but how can I go to PE2? Who is my next stop is decided by the IGP. And to go to P2, my best path is, let's say, P1. For P1, if I want to go to P1, I have to use level 400 because P1 told me this information, that if you want to come to me, use level 400. So it added level 400, but then 1, 2, 3, 4 is signaled by PE2 because PE2, this is called service level. PE2 has a service that is related to CE2, which can be a VRF. And it said to PE1, that means this adjacency is between PE1 and PE2, and it's not like level distribution protocol, LDP, that everybody will have to be connected to everybody, things like that. It's just a manually configured peering, and the PE2 said, if you want to reach CE2, use level 1, 2, 3, 4. So P1 added 1, 2, 3, 4 as the bottom stack or the lower stack. Now everybody in the middle will just look at this level. They don't need to look at this one because this one does not make any sense to them. So when it comes to P1, P1 said, remember P1, if I go back, P1's level mapping is if in level is 400, swap to 300. Because you need to go to the next one. Next one say my level is 300 and it send this level to here. So this time, if you can now map 400 when comes here, it will swap to 300. When 300 comes here, it will swap to 200 because again the level mapping happened before. And everybody is just swapping, not removing or popping any level. When it comes here, in PE2, it will see that this is the destination, so it will remove that level because after that there will be no level needed. And when it removes 100, it will look at 1, 2, 3, 4. It will understand 1, 2, 3, 4 is for my circuit, like towards CE2, and then it will finally be able to pass it to CE2. So in summary, normal switching, you just one level is okay, but when you want to do a service which can be a L3 VPN or L2 VPN or any other services, then you need to add like additional level, and you need protocol to pass those level. For the service level, it's good that BGP can do that. BGP is multi-protocol BGP, and BGP can run address families with MPLS or the VPN v4, VPN v6, or IPv4 or IPv6, and many other different VRFs you can run on top of MPLS. So this signal is done by BGP. These things done by routing done by IGP, but level done by LDP. So this is the whole kind of requirement at the moment with this picture. There can be many complicated scenarios, but with this picture, we understand that without LDP, I cannot run it. Without BGP signaling service, I cannot run it. With IGP, definitely I have normally for my internet. So IGP is there, it's okay.
So so the time when the packet comes from C1 to PE1.
Yeah.
And PE1 will look at the IPv6.
Yeah.
And know that the destination should be in PE2.
Yes.
Then inside the MPLS domain, they will no longer look at the IPv6. Just look at the label, is it?
Yes, yes. The IP information is here. Let's say the payload is here, and IP information is on top, but it's just look at the level instead of looking at the destination IP when it's switching. Actually, it looks at the IP, but then it does not process using the routing table. It processes using the level table. It's faster because they don't need to really look at a very long, very big routing table, and also the more upper layer information you need to process, the slower will be the performance or more resources will be needed. So looking at the level is faster for them to process, because you will see that even though if you have so many routes, you don't have level for all the routes. And it's also interesting that most of the routes comes from internet. So if you have a full routing table, you have a big routing table if you receive the full feed. But for internet, you probably don't need to add the levels, because level will only be assigned for the next hop, not the route itself. So this is how the routing table can be too big, but the level will not be that big list of routes there. So minimizing the searching in a small table is faster than searching in a big table. So your concept is correct, that PE1 will basically look at the level, add the level, and rest of the routers will basically look at the level and swap the level, and then finally come to PE2. It will again look at the level, and then once the level is done and it understands it's the destination, so it will then look at the routing table after the level switching part is done. So it will first look at the level, remove the level, means popping the level, and then finally look at the IP table, and then pass it to the CE2. Because here, if it does not look at the IP table, the packet will be dropped, because the destination is not reached. Destination is in the routing table, not in the level table or level LFIP. It's not there. So the last router will definitely need to look at the routing table. Yeah.
So when will they look at the label forward information table?
Yeah.
Where's
So PE1 will start looking at the LFIP, because it knows destination is this, and what is the level it needs to know. So it will look at the LFIP. Every single router in the middle will definitely look at LFIP. So what happens is it looks at the destination IP and then look at the level for that IP. So everybody needs to swap this number. That means they need to know the level mapping. So if 300, swap to 200. So that there is no IP information there. There's a level information. So everybody will look at LFIP table.
So how about the label 1, 2, 3, 4, and 400? Does C1 hop this label to?
So this one is to go to the next hop, and this one is the service level. It's called level stack. So level stack is a couple of levels together. Depending on the reason, the router will look at it. For example, for the next hop to go to PE2, my next stop is PE1, so I'll use PE1's level because PE1 understand that because PE1 is the router that told me that use 400 if you want to come to me to go to this destination. So PE2 said PE1 that if you want to come to me to go to PE2, use 300. So it has now a map in and out, like exactly the previous slide is the map. Yeah, here is the map. If you want to go to PE2, 400 is my level, so use 400. PE1 will use 400, but 400 will be swapped to 300 because PE2 told PE1, if you want to come to me, you have to use. So in that case, you just look at that table, not really look at the routing table anymore. So it's basically using the LFIP. So that is the entry. And this entry will be longer because there are so many other routers. They have also told that, my level is this, and this. So every single router in the MPLS domain will have this table in and out levels. So 300 is the top level. The top level will be swapped because the destination is not yet arrived. So the top level will be active till destination is arrived. So when it comes here, it knows that, oh, this is I'm the destination, so I have to look farther. So it will look down and it will see, oh, this is my service level, and I know this level, I configured it. So I know which VRF is pointing to or which VPN it indicates, and then it will look at the IP table to finally pass it as an IP packet by removing all the levels, restoring it back to its original shape, and then finally pass it to C2 because C2 will not understand the levels and it will not work if I still keep the levels and pass it to C2. And then there will be some more concept of how we can optimize it because there is something called PHP or penultimate hop hopping. It will come soon. But this is basically how it works. And there can be other services. More level can be in this stack. 3, 4. Every level takes 4 bytes of space. So the more level you have, the smaller the payload size becomes because your IP packets size is fixed. If you take longer space for header, the payload will be smaller. So, or you have to enable jumbo packet in the IP NTU. So that's why if you see MPLS operators, they put like very high NTU in their MPLS domain. It's usually 9012 or something like this. You can see that there because otherwise packet will be dropped. And in MPLS, at the beginning of the set configuring, you'll see that one of the big issue you will see that with the MTU, and this is not working. If I remove it, it works. So many of the troubleshooting happens around this one. But we're not going deep into the MPLS. Like I said, the SRv6 needs MPLS understanding better, so you understand this one. So I'm spending more time, but this is like a generic example. Actual deployment has really specific and a little bit more complicated setup. Vendor dependencies, interoperability, this comes into the picture when you really deploy it. Sorry.
Sorry. Yeah, please. Yeah, please. So the label 1, 2, 3, 4 carries another meaning.
Another meaning and signal by BGP. So you said here that he is my neighbor on this VRF. So let's say you can configure BGP with the address family indicating a VRF. So you are saying that this is a VRF and you want to do a peering with this one with BGP, and BGP can distribute level. So you don't need a new protocol for that. So, and because this does not share the information with any of the P routers, they don't even know that 1, 2, 3, 4 exists. So only it understands. This one only knows that if I want to go there, the source says use 1, 2, 3, 4. I'm just using it. I don't know what does that mean, but I know that to go there I have to use 1, 2, 3, 4. So the real packet moves based on the previous control plane synchronization. So control plane synchronization happened at the routing protocol level, and the level collected and build the ILM and things like that. But when the real packet comes, based on the table, the level will be stacked, and then it will go forward based on the level and finally reach the destination.
So the BGP is sorry. So the VPN is established by the BGP carrying.
Correct.
Okay.
Correct, because in MPLS, other routing protocols cannot carry this level. BGP can. Sorry, please go ahead.
Yeah, so is it something like the same as shortest path or?
Very good question. Very good question. I'm coming with this slide deck, but it's a good question. The question is whether the path will be based on the normal routing protocols decision, like shortest path, or whether suboptimal path can be taken. If I don't do anything, it will basically follow the routing, and that means shortest path. But there is one other thing. So that's called best effort, BE, and there is something called TE, traffic engineering, where I can navigate and steer the packet and take not shortest path, but the path that I want to take. So that's MPLS TE, or traffic engineering. It still exists for SRv6 as well. So I have some slides that covers that. So it will be, yeah. So but in short, without TE, it's just gonna take the shortest path. Actually, routing path, and routing takes shortest path. And that's why it's gonna take the shortest path. Now, here is something with the PHP, or penultimate hopping. Is basically saying that, when it came to, in the previous slide, when the MPLS packet came to PE2, I had 2 levels. But this is the destination, so this level even does not make any difference to it, because when this one was advertising, it said I don't have any out level. It's an implicit null. It's called implicit null, means I didn't learn it from anybody, so I don't have an incoming packet, incoming level. I'm originating it by myself. So actually, looking at 100 does not make any difference to PE2. It's the destination, so that 100 is meaningless to it. So this additional processing by PE2 is unnecessary. If P3, who is the penultimate hop, means the second last hop. This one is the last hop and this is the second last hop. If this guy remove it, then it will just receive 1, 2, 3, 4 and 1, 2, 3, 4. It's a little bit faster than processing 2 level. 1 level process is faster than 2 level processing. Okay, so that's called penultimate hopping. So the second last hop will remove the top level, but will keep the rest of the levels. Now there can be some cases where I don't want it. I want it to keep it like that, or at least I want the value removed but not the level removed. So that's called explicit null. You can ask the neighbor, hey, you remove it but keep this space, just fill it with 0. Explicitly fill it with null. This one has an implicit null, means it does not have any level after that. This one has an explicit null when you say